Okay. So, let us get into some of the details of this finite element method, and as I had mentioned much earlier, the conceptual way we work through it is actually very similar to what we have already discussed, this so called method of moments. Okay. So, let us just recap that. So, what was we had L phi of r is equal to f of r. If you remember, that was our operator equation on which we had studied the method of moments, right. So, to recap over here, what was L was an operator, right. So far the operators that we had seen were integral equation operators, they had an integral sign inside it. Okay. Phi of r was what? The unknown which I wanted, and f of r is a known forcing function along with some boundary conditions. Okay. So, all the boundary conditions are always need to be specified in this case. Right. So, we will assume the same sort of formulating equation over here as a starting point. What did we do when we went to the method of moments? What was the sort of step 1? Basis functions, right. So, I said okay, phi of r, I said I can write in this form a set of basis functions, right. And then what did I say? So, I substituted this inside. So, I got and this phi n and b n of r is equal to f of r, right. So, we could do that, but basically step 2 was what? Basis is one's first step, testing, right. So, I had, so these were basis functions and the next step was testing functions T m of r. So, what did I do? I took a inner product, right. So, take inner product. So, what happened? So, this summation stayed outside, right. This is n is equal to 1 to n. Okay. Phi n is a number that is constant, and here is where the testing function came. That is the left hand side, and right hand side simply became the inner product of right. So, this part is sort of familiar to all of you, right. Then what was the simplest kind of testing function that we considered? Delta, right. So, then if we take the simplest testing function, so that is T m of r is equal to delta of r minus r m, that is how I wrote it, right. So, this inner product and all of this stuff, what does it boil down to? This inner product collapses, the integral collapses, I am left with phi n, and then what will happen? What happens of the left hand side? L, okay, then Bn of r, what else? Where does the m appear? Or should I write, what should this, Rm. Any other suggestions? So, writing it as Bn of Rm is actually misleading, because Bn of Rm is a constant, right. Rm is a number, and if I apply the operator on a number, that is not the same as applying operator on a function. So, the technically correct way of writing it is evaluated at r is equal to Rm, means you make L act on B, and whatever you get, you substitute r is equal to Rm in that. Okay. And so, this is a shorthand way of writing it is you write Bn of Rm, but you should be clear what that means. Okay. And the right hand side becomes, here we can just write down, because this is a simple integral, this will become f of Rm. So, example is, for example, L can be something like the second derivative with respect to R. Okay. So, then this operator equation simply is second derivative of phi of R is equal to some function f of R, right. Now you can see why I have written this in this fashion, right. So, when I multiply this by some testing function, so delta of R minus Rm, and then that is the meaning of testing, right, the left hand side, right. So, this will become evaluated at R is equal to Rm, that is what it means. That is the only value that survives inside the integral, right. So, this was your testing function over here, and the method that we had, I mean the name for this was given as point matching, or what point matching was the name we had given, right, point matching. Okay. You could stop at this point, and this gives rise to a popular set of approximate methods which are called finite difference methods. So, this also leads to finite okay. So, what do I mean by finite difference methods? You can look at this example over here, right. So, here let us say that I do not want to calculate any analytical derivatives, and I have this second derivative of phi evaluated at one point, but I want to write this only in terms of function values, in terms of finite differences. Then what will I write this as? I mean this would then become something like phi of Rm plus 1 minus 2 times phi of Rm plus phi of Rm minus 1 divided by some 2. Yeah. So, this gives you one equation. So, this is f of Rm, right. So, like this you can repeat it for various values of Rm, and you will get a set of equations for every f of Rm on the right hand side, you get a set of equations. So, that is known by the name of finite difference methods. We will look at these in detail when we come to the third module of this course, okay. But I am just identifying a branch off point which happens right over here, okay. So, right. So, what happens is the same framework that we have for the method of moments is what we will use going forward for finite element method, okay. Question 2 delta R square, where Rm plus 1, oh, no, okay, you are saying is that what you are saying? Yeah, okay. I assume that the separation is 1, okay, that is, yeah, it is good to be more precise. Yeah, I mean, yeah, you are saying, you are asking what should be the separation between the node points. Yeah, so you have to be a little bit careful over here. You should be careful to make sure that you do not by default set this to just 2 and forget this term over here. It matters, okay, because overall your scaling overall whatever you do, it should be done in a consistent way, because as you have seen in integral equation methods before, as I make my discretization finer and finer, I get more and more accurate answers. So, that discretization translates into the distance between nodes. So, I am approximating a derivative by a finite difference, right. So, that the denominator matters. So, you have to be careful about it. People who do not include this factor here in the denominator, they include it in the numerator of the on the right hand side. This is just by, I mean the idea behind this equation is finite difference approximation of a derivative. Forward difference, central difference, backward difference, those are ways of approximating a derivative. You apply it 2 times, you get this expression. Okay. But yeah, we won't go more into this because we will have a dedicated module for studying finite difference methods. Okay. Okay. So, this is the same framework that we are going to use, okay, and coming more towards the FEM, right. What FEM does is it sets the testing function to be equal to the basis function. Okay. So, that is the most, I mean, it is not an absolutely golden rule, but it is by far the most common way of doing FEM is you choose the testing and basis functions to be the same. Okay. And this is also called, we had come across this word earlier, Galerkin's method. Okay. So, just one thing I want to point out from the previous slide, when I look at this equation over here, I can also rewrite, I mean, I can rewrite this whole equation in an even simpler format like this, which is L of f r evaluated at r is equal to r m is equal to f of, sorry, this should not be f, this should be phi, right. This is one and the same equation, you agree? So, in some sense, what am I saying with this equation is that I am enforcing this equation at a few discrete points r1, r2, r3, rm, correct, right. So, if I had my whole axis like this r, I am only enforcing it at some regular grid of points over here, but I am not saying anything about what happens at intermediate points over here, here and so on, right. So, the natural question is that is there a way to get little bit more accuracy? Okay. So, what we can do with this is this same equation that I had, L of phi of r is equal to f of r. Okay. What I will do is, let me rewrite this in the form like this, L phi r minus f of r is equal to 0. Okay. Previously, we were enforcing this at just 1 point. Now, what we will say is, to get better accuracy, I am going to use a testing function other than a delta function, and that is the same as the basis function in FEM. So, what does that basically mean? It means that an integral over, so BMR this is testing, right. This is the same as step 2 earlier, testing with a basis with a testing function. In this case, the testing function is the same as the basis function, right. So, I will continue to write phi of r as this n is equal to 1 to n phi n of b n r. Okay. What is the domain that we have? Let us say this is the computational domain, let us call it capital omega. Okay. Now, throughout FEM, one of the sort of key features is that these basis functions or testing functions, they are subdomain functions, means they are non-zero only over some small region. Okay. So, subdomain basis and testing functions. Okay. So, in principle, this integral is over the entire thing, but it does not matter because Bm is non-zero only over some small region, right. So, let us say that this is the region where this Bm is 0. Okay. So, we can call this non-zero, sorry, this is sigma m. Okay. So, this is we call it the support of Bm of r. Support means the region in space where it is non-zero, outside it, it is 0. Okay. So, in that first picture where you saw that aircraft which was sort of broken up into triangles, each triangle is like this one sigma m, omega m. Okay. That is the idea. Will be composed of little such things. Okay. So, now when we started by saying that the earlier method was enforcing this delta testing, it was enforcing the differential equation at a few discrete points. Now, what am I, can we give an interpretation to this equation? So, this is the differential equation I want to enforce. So, this is, I can view this as a residual. If this is non-zero, that means the differential equation is not being fully obeyed, correct? And I can view this as a weight for this overall integral. So, now I am saying, okay, I am not insisting that this residue will be 0 at every point in space, but in an average weighted sense over this domain omega m, enforce it to 0. Okay. This is very different from saying that L phi of r should be equal to f of r for every r. That is too strong a condition. So, we are weakening it, we are saying okay, you can, I will allow you to have it go to non-zero values or in an average sense. For example, if Bm of r was 1, like a pulse function, then what am I saying? The average residual is 0. That would be the meaning of this equation, right. But in general, Bm of r need not be just a pulse function, it can be something more complicated. So, the reason I am giving this slightly different interpretation is because the FEM community, it's like giving a interpretation to the method of moments equations which we had already derived. So, here when we had derived the method of moments equation over here, we did not have this weighted residual interpretation, right. We just said okay, phi is projected on basis B, then I do testing along Tm. That was my interpretation, we were happy with it. The finite element people, they arrived at the same equation via a slightly different route, and their interpretation is weighted residual. The equations are the same, this is a interpretation given is different, okay. But if you read papers and textbooks on FEM, they will call it a weighted residual method. When you read that, you shouldn't get confused, you should realize it's basically MOM, method of moments, right. The same thing is being called by different names and different phrases. The concept is the same, basis function, testing function. So, yeah, we are enforcing it to be 0 in a weighted sense.
So, if you take omega, it will not be.
It will be because Bm is 0 outside omega m. Bm, right, Bm is 0 over here. So, it does not matter. You can as well call this omega, it does not matter. Okay. So, now your phi over here is coming from this expansion in the basis functions. So, how many unknowns in this equation? N equations. How many n equations and how many equations? How many equations is this? I mean, this is just one equation. For a given choice of Bm, this is one equation. So, what the basic framework of FEM is, break up your whole domain into such, such exactly, whatever, dot dot dot, right. So, repeat for m is equal to 1 to n, and you get a system of equations Ax is equal to, we will call it C, okay, and where your x's are what? Ax is going to be a column vector phi 1, phi 2 all the way up to phi n. That is my unknown. Every testing function gives me one equation, and I have n such testing functions. So, that's the sort of philosophy that we use. How do we choose these basis functions? So, the finite element method needs that these basis functions, they should have certain properties of continuity and differentiability, okay, which we will come to later. Okay. So, just to tell you that you can't choose these, you should not choose these BMs in some random fashion, they should have some nice mathematical properties. Okay. Continuity and differentiability are some of the popular ones that these functions should have. Now, so far I have been writing this as a very abstract L operator kind of a thing, but we want to see something more concrete. So, what could be an example of this L operator? Okay. So, very simple example, Maxwell's equations, the first two Maxwell's equations we know we can eliminate one variable like E and H, I can eliminate H and just write it in terms of E, right. So, for example, what was your curl of E? Curl of E was minus j omega mu H of R, okay, and mu is also a function of R in general, okay. Now, if I wanted to use the next equation, what should I do? If I take a curl over here on the left hand side, can I use the curl on the right hand side? No, because I know curl of H, I do not know curl of mu into H, right. So, what I can do is, I can exactly, I will remove this from here, I will do 1 by mu r, right, and the next equation is del cross 1 by mu r del cross E of r is equal to minus j omega. Curl of H is j omega epsilon r E, right, and a plus j term, assume j is 0, okay, let us just make j is equal to 0, it is not much of a complication. Okay. So, let us write it actually, need not be, it is easy to deal with it, right. So, this whole thing can be simplified as del cross 1 by epsilon r, I will just keep the relative permittivity, del cross E is and a minus. So, all of this omega squared, epsilon naught, mu naught, all of that simply becomes a k naught squared epsilon relative permittivity E. Okay. So, what you have now on the left hand side is actually your operator L, right. So, operator L is what, del cross 1 by epsilon r which is a function of space, del cross minus k naught squared epsilon r of r, I can write it like this, yeah, yes, this should be 1 by mu, I like epsilon so much. Okay. So, this is an example of my L operator and this is my phi. Okay. If I had a current term, where would it go? This J term, if it were non-zero, where would it go? It would be my F on the right hand side, right, because there would be no electric field or anything, it would come on the right hand side. So, we have seen examples of non-zero right hand side, but the main difference that you can observe in this equation from what we have already studied is what? There is no integral equation in the operator, I mean there is no integral sign in the operator, it is purely made out of what? Derivatives, right. Yeah, it will come in place of 0 on the right hand side, okay. Yeah, in fact, yeah, it will be minus j omega j on the right hand side if current was non-zero. So, this is sort of to sum it up, this is your the basic setup of finite element method is that first of all the basis functions are subdomain, that is a key point. Next, your operator is a differential operator, therefore, there is no Green's function involved in its solution. The moment I got an integral equation, I mean Green's function will appear there as the solution, okay. And the sparse part is not clear from this, but we will come to it as we take up examples, okay. And so, this is the basic framework with which we will sort of go ahead and study the finite element method more, okay. So, subsequent modules will look at what are the examples and cases for this Bm of R, how will we arrive at a sparse system of equations, how do we solve it with 1D and 2D examples, okay. Any questions on this so far? So, you notice that in in every single new method that we come across, we always just start from Maxwell's equations and either take it through a differential route or an integral route and then different methods come from there. Starting point, all you need to know is Maxwell's equations, little bit of vector calculus.